inviting us for this faculty interaction webinar series on ab initio modeling and design of 2D materials using the Synopsys Quantum-ATK. So let me first share my screen. Is my screen is clearly visible?
Yes, sir.
Okay. Yes, sir. Thank you. So my name is Dr. Sayan Kanungo. I'm presently working as an assistant professor in BITS Pilani, Hyderabad campus. Today, me and my research scholar, Ms. Shivani Reddy, will be discussing the ab initio modeling and designing aspects of 2D materials for supercapacitor electrode design using Quantum-ATK software. So before beginning with the main content of the presentation, let us briefly look into the outline of today's talk. So first we will be giving a general introduction to the ideal supercapacitor electrode design, where we will be focusing on the basics of supercapacitor and the electrode design aspect. This would be followed by a brief discussion of how the Quantum-ATK can be utilized for 2D material-based supercapacitor electrode design, focusing on the surface modification technique in 2D exin as our case study. Finally, we will be highlighting some of our recent research on this domain, and we will briefly introduce our research group. So let us begin with the presentation. So initially, we will begin our discussion with some important milestone related to the development of the supercapacitor. As the name suggests, the supercapacitor is a form of capacitor that can store electrical energy. Now, the capacitor is known as one of the forerunner of the energy storage device, where it was observed more than a century ago that as simple as a structure like two metal plates separated by a insulator region. Just a second, let me take this one. So two metal plates separated by an insulator region can efficiently store electrical energy. So the modern capacitors, the major technological development in modern capacitors started in 1950, where the porous carbon electrodes followed by the activated carbon electrodes are introduced into the design of electrolytic capacitor. Following this development in the modern capacitor, the concept of the supercapacitor was first introduced around 1982. And in one of the major demonstration in this effect was the hybrid electrolytic and electrochemical capacitor, which was demonstrated in 1994. However, the modern supercapacitor came into existence much later, and it was around 2010 the modern supercapacitor was successfully introduced and thereafter incorporated in the industrial application. Now, in modern supercapacitor, the charge storage mechanism is principally based on two distinct processes. One is electrochemical charge storage mechanism and another is electrostatic charge storage mechanism. For this specific talk, I will be highlighting on this electrostatic charge storage mechanism, and this type of supercapacitor, as the name suggests, are called electric double layer supercapacitor. So let us very briefly discuss about the supercapacitor for the general audience over here. The first question that we should be asking, what is supercapacitor? As the name suggests, the supercapacitor is a form of capacitor. However, the prefix super definitely indicate it is something beyond the normal capacitor. So indeed, if we like to give a simple definition of supercapacitor, we can view supercapacitor as a capacitor with a high capacity whose capacitance value is much more larger than the solid state capacitor with lower voltage limit. Now this supercapacitor basically bridge the gap between the electrolytic capacitor and rechargeable batteries, where the introduction of supercapacitor shows us some distinct properties associated with supercapacitor, namely high power density, faster charging and discharging, wide temperature range operation, and the absence of memory effect. So based on this distinct feature of supercapacitor are rapidly gaining attention from the different application area, and today the major application area of supercapacitor include consumer electronics, power generation and distribution, transport and defense. So as we have very briefly touched upon, the supercapacitor basically work on the two distinct type of charge storage mechanism, and based on this charge storage mechanism, the supercapacitor can be broadly classified into electrostatic supercapacitor and electrochemical supercapacitor. But before going into this, I would just like to mention there are also a third type of supercapacitor, which is a hybrid between the electrostatic and electrochemical supercapacitor. In an electrostatic supercapacitor, the charge storage is basically achieved through a formation of the Helmholtz double layer. In this Helmholtz double layer, the electrostatic charge storage leads to a large capacitive value for the supercapacitor. In contrast to this electrostatic supercapacitor, in electrochemical supercapacitor, the charge storage is basically based on the principle of Faradic charge transfer, and in a hybrid supercapacitor, both the double layer formation and Faradic charge transfer take place simultaneously to enhance the overall capacity of the supercapacitor. However, as indicated in this particular discussion, we will be focusing on the electrostatic supercapacitor. So this electrostatic supercapacitor are also known as electric double layer supercapacitor. Let us briefly view the operation of this supercapacitor. Just like a simple battery, the supercapacitor, or for that matter, just like a simple capacitor, the supercapacitor can be perceived in its charge state and discharge state. Let us try to look how this supercapacitor can be schematically represented in their discharge state. In a discharge state of supercapacitor, we can see the two electrodes are separated by a electrolyte where the dissolved cation and anions are randomly distributed over the extent of this electrolyte. And between the two electrodes, there is a solid separator that are usually introduced in the supercapacitor structure. Now these things become much more interesting when we apply a potential difference between the anode and cathode electrode, which leads to a schematic representation of the physical mechanism, something of this sort. So what happens when a potential difference is applied between the two electrodes? Based on the polarity of the potential applied to an electrode, the opposite charge polarity ions or the counter ions try to reach towards that particular electrode. However, in this ideal supercapacitor, if we look closely, we will be able to observe that counter charge ion are physically separated from the electrode surface by a molecular layer of solvent molecule which are polarized in nature and which are physio-adsorbed on top of the electrode surface. So this basically forms the electric double layer, from where the name electric double layer supercapacitor was derived for this type of supercapacitor. So if we look once more into the details of this electric double layer, we'll be able to identify there are two charge layers in this electric double layer. One charge layer is formed due to the dissolved ion layer in the electrolyte, which are in the close vicinity of the electrode surface, and the other ionic layer is basically constituted of the charge layer at the surface of the electrode material. Now these two layers are physically separated by the polarized solvent molecule between them. Usually a monolayer of solvent molecule physically separated these two layers, and these polarized molecular solvents are basically polarized solvent molecules are basically act like a molecular dielectric layer. So from a very basic understanding of a parallel plate capacitor, if we just draw a simple analogy, we can argue that two charge layers are separated via ultra thin dielectric layer, which also happens to have a very large dielectric constant. So this is basically lead to a efficient energy storage between these two separated charge layer, and that is basically the governing principle of electrostatic charge storage in the ideal supercapacitor. So the performance of this type of supercapacitor, from this simple discussion of their operating principle, we can deduce that the performance of this type of ideal supercapacitor depends on the both electrolyte and electrode specification. So let us also look into some of the design aspect of the electrode. So in here, we are basically going to focus on the electrode design aspect. So let us see how the properties of the electrode influence the performance of ideal supercapacitor. So as we all know, one of the major challenge of the supercapacitor technology is its relatively low energy density. Compared to batteries, the supercapacitor gives a large power density. However, compared to the same conventional battery, the supercapacitors fall short of the energy density aspect. So recently there is a, oh, before that I'd just like to indicate that this energy density in the supercapacitor is directly related to the specific capacitance of the supercapacitor. So recently there is a lot of effort that has been observed where the specific capacitance improvement was one of the major focus of the supercapacitor research. So in this context, one of the most promising strategy for improving the specific capacitance of the ideal supercapacitor is to engineer the electrode material of the supercapacitor. Before going into this engineering aspect of the electrode material of the supercapacitor, let us briefly summarize what are the most desirable property of an electrode material in a supercapacitor. Our electrode material of a supercapacitor should be able to demonstrate high electronic and thermal conductivity. It should be stable over a range of operating temperature, as well as it should be chemically stable. Now, it should also be able to demonstrate a large specific surface area. And finally, the electrode material should preferably be synthesized through a low cost process, and the material itself should be environment friendly in nature. So all this requirement is basically leading to a very recent exploration where one of the emerging material system or one of the emerging nanomaterial known as two-dimensional materials has been investigated for the ideal supercapacitor electrode design. So the distinctive feature of this 2D material system that has encouraged the research on 2D material based supercapacitor electrode design includes large specific surface area, few atomic layer thickness, tunable electronic properties, as well as tunable thermal and ionic conductivities. However, in spite of all these advantages, like any other nanomaterials, the 2D materials also encounter a severe technological bottleneck due to its one of the intrinsic property, which is known as quantum capacitance. So we are going to elaborate on this aspect in the next slide. So if we look in general into the total interfacial capacitance of any ideal supercapacitor, it basically have two capacitive element in series, which is the electric double layer capacitance and quantum capacitance. Those who are absolutely new to this area, for them I'd just like to very briefly explain this aspect. It is similar to a situation if I have a simple parallel plate capacitor and one of the metal plate, if I replace with a material which have a lower density of state. So then the total capacitance cannot be given in terms of the simple capacitive formulation that we all know, capacitance equal to area into permittivity by the separation between the electrode. So there, this second component, the quantum capacitance, will also come into the picture. The situation is very similar for the ideal supercapacitor as well. This quantum capacitance is one of the major concern in the ideal supercapacitor design, and this quantum capacitance basically represents the intrinsic electrode capacitance, and which strongly depends on the material properties. Specifically, the quantum capacitance have a strong dependence on the material properties like density of states, effective masses at the band edges, energy band gap, and the Valley degeneracy factors. So this quantum capacitance, as I said earlier, poses a significant design challenge for the 2D material-based electrode design for the ideal supercapacitor due to the intrinsically low density of states in the 2D material. The quantum capacitance in the 2D materials are usually much lesser than the bulk metals. So this leads to a situation where the total interfacial capacitance becomes significantly lesser than the electric double layer capacitance. So here, let us just take a small pause and try to visualize what we are trying to convey over here. If I consider an ideal supercapacitor, its total interfacial capacitance should be very much comparable to the electric double layer capacitance, because the large capacity of the supercapacitor is basically driven by this particular capacitive element. However, the presence of a low quantum capacitance represents a very detrimental effect in this ideal scenario. Due to the presence of low quantum capacitance component, the total interfacial capacitance falls significantly short in values compared to the ideal capacitance. So this major bottleneck in 2D material-based ideal supercapacitor design is basically stumble the progress in this particular aspect, and one of the major thrust area of the research for the 2D material-based ideal supercapacitor performance improvement is to apply suitable engineering strategies in the 2D material to improve their overall quantum capacitance without compromising their other favorable properties which are necessary for ideal supercapacitor application. Now, this is the precise juncture where the theoretical investigation start playing a major role. How so? Let us try to explore that. So the theoretical investigation is basically started acting like a anchor for or guide for the experimental exploration of different engineered 2D material for the ideal supercapacitor electrode design. The theoretical investigation can reliably predict and thereafter screen the potential 2D material system which are much more suitable for the ideal supercapacitor electrode design. And also the theoretical investigation can successfully identify potential material engineering strategy and quantitatively assess their efficiency for ideal supercapacitor electrode performance improvement. So based on the theoretical investigation, the potential material systems, potential 2D material system and the potential material engineering strategies for those 2D material system can be identified. So this makes the job of the experimentalist much easier in the sense that the theoretical investigation is both cost effective as well as time effective. So from a larger set, the theoretical investigation brings down the potential material system into a smaller subset over which the experimental exploration can focus on. However, the complementary nature of the theoretical investigation and the experimental exploration are not only limited in the material screening and the material engineering technique identification. Once the 2D material is successfully integrated in the ideal supercapacitor electrode design, the performance of the ideal supercapacitor can also be analyzed in connection with the theoretical investigation, where a direct correlation between the atomistic property of the 2D material system can be offered with the experimentally observed performance of the ideal supercapacitor based on 2D material. So now the question that we should be asking at this juncture, how these theoretical investigations are actually being performed. The theoretical investigations are basically based on density functional theory based first principle calculation approach. And quantum ATK, synopsis quantum ATK, is one of the most reliable tool to achieve this theoretical investigation, which can thereafter be successfully integrated with the experimental exploration in this effect. So these density functional theory based first principle calculations are considered as an emerging research technique for performance assessment of novel material system like 2D materials or engineered 2D materials for the electrode design and optimization. The density functional theory based first principle calculation, as most of us aware, is basically performing a theoretical experiment on the material system. Since the name suggests the first principle or ab initio calculation, the user just have to specify the details of the material system, namely its elemental composition, crystal type, and thereafter the density functional theory based first principle calculation can calculate number of relevant properties associated with the material system. And for this particular aspect, the most important properties that are associated with the 2D material based electrode design for ideal supercapacitor are the structural stability of the 2D material, the electronic properties of the 2D material. These two are the primary properties that any theoretical investigation will first aim to investigate. So we are going to elaborate on this aspect further. Here we are going to show the generic computational methods overview where the quantum ATK based 2D material simulation can be integrated in the theoretical design and modeling of 2D materials for ideal supercapacitor electrode design. So the first step in this aspect would be to consider a potential 2D material system which satisfy most of the requirement of a superior electrode material, and thereafter identify the suitable material engineering strategy which will lead to a engineered 2D material. So after having this engineered 2D material, the relevant properties of this engineered 2D material can be methodically investigated, which once again I am repeating, which include the structural properties, surface properties, electronic properties, as well as the stability aspect of this engineered 2D material. So once the properties has been successfully explored, then the electronic properties can be extracted from this simulation and can be introduced into a standard analytical calculation framework. Using that calculation framework, the electrode performance can be numerically calculated, which will lead to a performance metrics like excess charge density, quantum capacitance, and total capacitance. So let us try to briefly understand this particular aspect of the calculation, because the density functional theory based calculation, as I believe, has already been covered in the initial part of this interaction webinar. So I'm not going to go into the details of that aspect. Rather, for the 2D material based electrode design, it is essential to have a overall understanding of this standard analytical framework that are being used by the theoretical groups to assess the electrode performance of the 2D materials. So we will start our discussion from the quantum capacitance. What is a quantum capacitance? As I mentioned before, the quantum capacitance is the intrinsic capacitance of the 2D material system, which can be viewed as a rate of change of excess charge density with respect to the local electrode potential. Now, under quasi-equilibrium condition, the quantum capacitance can be expressed by this particular expression, which involves two distinct factors, namely the density of state, which represent the material property of the 2D material system under question, and the second factor is the thermal broadening function. This thermal broadening function is given in this particular expression. The thermal broadening function is basically represents the inhomogeneous carrier density, the broadening in the energy level due to inhomogeneous carrier density distribution because of the electron hole puddle induced by the local potential fluctuation in the lattice, as well as possibly finite lifetime of the electronic states associated with the lattice under question. So, just like the quantum capacitance, the excess surface charge density can also be numerically calculated following this expression, where once again we will see the density of states is remaining one of the major factor of determining the excess charge density. The other factor is basically the difference between the Fermi-Dirac distribution function of two electrode, which is an explicit function of the local electrode potential. A closer observation to both of these expressions will reveal the quantum capacitance and the excess charge density are an explicit function of the local electrode potential. So once this density of state profile as a function of energy is calculated through the DFT calculation using quantum etiquette, it can be directly introduced into this expression and can be numerically evaluated, which will give a set of quantum capacitance and excess charge density values for a range of local electrode potential. So these are some of the reference based on which these standard analytical frameworks were represented here. Now we will go to the next stage of this discussion, where we will be demonstrating the 2D material for electrode design, and this section will be presented by Ms. Reddy. So over to you, Shivani.
Thank you, sir. First of all, I would like to thank the organizer as well as my supervisor for having me here. So without no further delay, I'm going to start with the presentation. Is my screen visible?
Yes,
Yes,
Shivani.
yes, yes.
Yes,
So once again, good evening, everyone. Until now, we have seen the evaluation of supercapacitor and what is supercapacitor, its introduction, and what are the major challenges in supercapacitor. Now, we are going to see with the demonstration of 2D materials uh, for electrode design of ideal supercapacitor using quantum etiquette software. Here, we are going to see 2D exines as representatives of 2D materials for electrode design of ideal supercapacitor. But before that, what are these 2D exines? 2D exines are 2D materials made out of single element, and these 2D exines can be broadly classified into Dirac exines and non-Dirac exines. Dirac exines are typically the exines which are called as the semi-metallic exines, where the conduction band minima and valence band maxima touches each other, giving rise to a semi-metallic nature. In contrast, non-Dirac exines can either be in semiconducting or metallic in nature. That means it can either have a finite band gap near Fermi level, or conduction band minima and valence band maxima can overlap with each other. So, in this presentation, we considered one example from each category, that is graphene from Dirac exine and phosphorine from non-Dirac exine. Now, let us first concentrate on graphene. Graphene is having a hexagonal honeycomb lattice with perfect planar structure, wherein phosphorine is having a kind of buccal structure with orthorhombic face. So, if we consider the energy band diagram of graphene, as we have stated before, the conduction band minima and valence band maxima are touching at a point which is known as Dirac point. Point to be noted in this case is that near the Dirac point, the energy versus momentum relation is linear in nature. While touching conduction band minima and valence band maxima at Fermi level, causing a zero band gap is definitely advantageous for ideal supercapacitor electrode design. However, the presence of linear EK relationship leading to a smaller density of states near Fermi level, which is again a disadvantageous aspect for graphene. In contrast to graphene, phosphorine is showing semiconducting nature from its band structure, providing a finite band gap around the Fermi level of phosphorine. However, if we see the EK relationship near conduction band minima and valence band maxima, phosphorine is showing a non-linear relationship which is highly advantageous for ideal supercapacitor electrode design, but leading to a larger band gap, which is again a major challenge in phosphorine. So, to summarize this assessment, we can say that in graphene, touching of conduction band minima and valence band maxima ensures the presence of new electronic states near Fermi level. However, the EK relationship of graphene leads to a smaller density of states near Fermi level. Similarly, for EK relationship of phosphorine, we can say that within some energy window around Fermi level, there are no electronic states present. So, beyond conduction band minima and valence band maxima, there will be larger density of states which will be advantageous for electrode design of ideal supercapacitor electrode design. This will surmise the inherent advantages and disadvantages of both graphene as well as phosphorine. But what about the inherent disadvantages? So, from this context, the concept of material engineering techniques comes into the picture, where we can apply suitable material engineering techniques for both graphene and phosphorine to address their inherent limitations. If we look from the context of graphene, if through some material engineering technique, a non-linearity in EK relationship as well as localized density of state peak near Fermi level can be introduced, which leads to a notable improvement in quantum capacitance. Whereas for phosphorine, if we can reduce the energy band gap of phosphorine at same time introduction of some localized density of state peak near Fermi level, through some surface modification technique can significantly improve the overall performance of ideal supercapacitor. In this context, let us look into the few surface modification techniques like substitutional doping, surface decoration, defect engineering, which can significantly influence the electronic properties of 2D exceeds. These surface modification techniques are used for meeting up the specific objective, that is, altering the band gap and in shifting the conduction band minima or valence band maxima with respect to Fermi level. It can induce dispersionless bands near Fermi level, or it can alter the EK curvature near conduction band minima or valence band maxima. The overall essence of this matter is that either of these material engineering strategy are expected to tune the density of state profile near Fermi level. For that, a detailed theoretical understanding of different surface modifications in different exenes will not only screen the suitable exene material for 2D electrode design, but also identify what will be the potential material engineering strategy that will lead to a superior quantum capacitance for the material. So, from this perspective, the DFT-based ab-initio calculation has emerged as the potential theoretical technique to address this concern. However, to date, only a handful of exploration is done in the literature through different surface engineered 2D materials as electrode design for ideal supercapacitor. Now, let us look into the theoretical state of art for different 2D materials. Here, we are not confining ourselves to only 2D exins. We are going to see with the literature for different 2D materials. However, we'll start with 2D Dirac exins first. That we'll start with the graphene. We can see the exploration of material engineering strategy in graphene for EDL supercapacitor electrode design has started somewhere around 2015. And to date also there is a consistent research effort taking place through different surface modification techniques to improve the quantum capacitance of graphene. Now, the other prominent 2D Dirac exine is germanium. The similar kind of exploration of surface engineering techniques have been done on germanium like graphene, which also have shown the notable improvement in quantum capacitance and improved the overall performance of EDL supercapacitor. Now, let us focus on the 2D non-Dirac exine, that is phosphorine. Phosphorine is relatively a new material in context of EDL supercapacitor electrode design. As the timeline shows here, the exploration of phosphorine has started somewhere around 2021 and thereafter only a handful of work has reported. Apart from 2D Dirac exines and non-Dirac exines, TMDs are the other class of 2D materials used for electrode design of EDL supercapacitor. TMDs exist in its 2H phase and 1T phase. As we know, Group 4 and Group 6 TMDs exist in both 2H and 1T phase, wherein 2H phase is shown semiconducting nature, whereas 1T phase is showing metallic nature. Metallic nature are particularly exploited for EDL supercapacitor electrode design in recent literature. Finally, apart from TMDs, MXins are also recently started being explored for this application. However, it is worth noting that similar to phosphorine, both TMDs and MXins are very less explored materials in literature. So, from this context, let us try to understand a basic workflow of 2D material-based electrode design of EDL supercapacitor. So let us first start with our primary material, graphene. To start with, first we need to build up a supercell of graphene in the builder of quantum ATK software. Once the supercell is built, we have to geometry optimize it to get the minimum force tolerance per atom and the lowest energy. Thereafter, the optimized 2D exine has to be performed with DFT simulations for calculating both the EK structure as well as density of states profile, which can be viewed using virtual nanolab GUI of quantum ATK software. So once if these properties are realized, then density of state profile can be utilized under the mathematical framework as shown here. This is used to determine the excess charge density as well as quantum capacitance profile of graphene. As we can see here, after the post-processing of DFT simulated result, we can obtain excess charge density versus local electrode potential and quantum capacitance versus local electrode potential profiles. A closer observation to this profile reveals that both excess charge density as well as quantum capacitance profiles are significantly lesser within standard local electrode potential. Now, the question is, how can we improve this particular nature of low excess charge density as well as quantum capacitance in graphene? That is with the help of surface modification techniques. First, let us look into the defect engineering. In this demonstration, we have considered a supercell of graphene and we have introduced a single carbon vacancy in the supercell of graphene. And then we have to geometrically optimize the structure in quantum ATK builder, and with the help of the DFT simulations, we can calculate the electronic properties in quantum ATK software. As our results indicate, the presence of single carbon vacancy notably influence the EK structure near Fermi level of graphene. Here we can see that linearity of graphene is notably compromised by presence of carbon vacancy, and also carbon vacancy introduced dispersion-less bands near the Fermi level. So, which leads to an introduction of large localized peak in density of state profile of defect engineered graphene. This large peak leads to large excess charge density as well as quantum capacitance. Again, this excess charge density as well as quantum capacitance profiles are calculated with help of mathematical framework shown here. If we see the magnitude of both excess charge density as well as quantum capacitance of carbon vacant graphene with respect to the pristine case, we can see a significant improvement in the overall performance of graphene. So, this tells us that carbon vacancy in graphene is basically beneficial for ideal supercapacitor electrode design. Moving on, next we are going to see the substitutional doping. In substitutional doping, rather than creating a carbon vacancy, we are just replacing a host atom with dopant atom. Either it might be non-metal or metal, and we have to geometry optimize the structure with the help of quantum ATK builder, and with some DFT calculations, we can calculate electronic properties with the help of quantum ATK, and excess charge density as well as quantum capacitance profiles are calculated manually with the help of mathematical framework shown here. And the results from both substitutional doping as well as defect engineering shows that introduction of surface modifications are showing a prominent result for ideal supercapacitor electrode design. Now let us go to the future scope. Now I would like to summarize the future scope of quantum ATK based theoretical exploration of 2D material for ideal supercapacitor electrode design. First thing we can observe is that since the TMDs and exenes are less explored materials, the effect of defects in these exenes and TMDs can lead to a very significant improvement in overall quantum capacitance. Now coming to the exenes, the surface functionalization, specifically surface absorption of different functional group as well as element, could be a potential way towards optimizing the overall performance of exene. And finally, the artificial 2D material, for example, the van der Waals heterostructure between two dissimilar 2D material can also be explored as a potential strategy for improving the overall quantum capacitance of 2D material. So these are the broad overview of the possible future exploration for this kind of research. Next, the group research highlights will be presented by Sir. Thank you.
Thank you, Shivani, for the nice demonstration. So I will share my screen. I hope my screen is clearly visible.
Yes, sir.
So let us very briefly look into some of the research highlight related to this particular domain from our group, as well as a brief introduction of our research activity. So I will start with the recent research publication on 2D material based ideal supercapacitor electrode design from our group. The first publication that we have published in the Journal of Energy Storage in this domain is particularly aiming at the substitutional non-metallic doping in black phosphorine for the overall ideal supercapacitor electrode performance improvement. So in this specific work, we have particularly focused on the boron carbon doping and co-doping strategies, and our investigation revealed that the introduction of the carbon doping is highly advantageous for the overall ideal supercapacitor electrode performance improvement. Specifically, the introduction of carbon leads to delocalized defect states in the near about the Fermi level of the black phosphorus, and which essentially transform into a large peak near the low electrode potential, low applied local electrode potential range of carbon doped phosphorine. So this particular work has basically provide us a very clear understanding of what type of dopant and what specific type of modifications are most suitable for the semiconducting exins material for their quantum capacitance improvement. The next research in this particular domain that I'd like to highlight is the ideal supercapacitor electrode design for graphene, where the group 6b and group 10 transition metal atoms are surface adsorbed and substitutionally doped in graphene. And from this extensive comparative study, we have been able to identify that the adsorption of group 6b transition metal, namely the chromium, molybdenum and tungsten, as well as the substitutional doping using this group 6b transition metal, leads to large localized peak in the density of states near Fermi level, which once again transform into a overall improvement in the quantum capacitance of the graphene. And when we have looked into the total interfacial capacitance with respect to ideal capacitance value, we have observed that for a standard range of ideal capacitance value, the total interfacial capacitance has been significantly improved after introducing this specific group 6b dopant and surface adsorbent in the graphene. So moving on, we'll just very briefly introduce our group's thrust research area. Our computational nanomaterials and nanodevice research lab is focusing on two specific areas, namely the computational nanomaterials design as well as computational nanodevice design. From the perspective of the computational nanomaterial design, we employ Ab-initio DFT calculation-based material modeling and design technique. And the three vertical, the technological vertical in which we work on are the sensing, energy storage and electronic. In case of sensing, we are particularly focusing on the surface modified 2D exins and 2D TMDs. And for this domain, we are also working with the small molecular probes, and we design these molecular probes through functional group engineer to have a superior sensing performance out of these materials. Now moving on to the next vertical in the energy storage, as we have already discussed, we are working on the supercapacitor electrode design. Apart from the supercapacitor electrode design, we are also working on the battery electrode design for the lithium ion and other post lithium ion batteries. In the electronics aspect, we are working on the electronic and optoelectronic property engineering using the artificial 2D material system like Janus transition metal dichalcogenides, the van der Waal heterostructure between the transition metal dichalcogenides. And very recently, we have started working on the nanostructured bulk topological insulator material, and we are trying to simultaneously tune their surface and the bulk electronic properties through suitable material engineering strategies. Apart from our independent theoretical investigation, we also collaborate with the experimental research group in BITS and outside, where we are mainly focusing on complementing the experimental findings in the domain of strain pressure sensor design, electrochemical gas sensor design, optical biosensor design, and photodetector design. So our research team is consist of these people. Out of them, two of the research scholar has already been awarded their doctoral degree, Dr. Josna and Dr. Aditya. There are five research scholars who are presently working towards their PhD degree in their respective domain. Finally, to conclude this discussion, I'd like to acknowledge our research collaborator from India and abroad with whom we are collaborating on the multiple aspect of nanomaterial design and modeling. So thank you. I'd like to take questions from the audience if there is any. Shall I take the questions directly? Okay. So I think somebody just raised hand.
Good evening, sir.
Good evening.
Sir, actually, we are looking to work with the quantum ATK software. So I have some question about the quantum ATK software. First question is, for which type of material quantum ATK is more suitable? Another question is, can quantum ATK works on a standalone computer or it require HPC? And can you also explain about its licensing?
The licensing part, I don't think I'll be the right person to explain.
Okay, sir.
So,
Okay, sir. Thank you.
So just to very quickly sum up your first question, quantum ATK can be used for a wide spectrum of material system. It is not only applicable for 2D material. You can work on any bulk material, nanomaterial. 2D material is one of the nanomaterial. You can even work with the small molecular system as we are working. And I think the present license of quantum ATK are also enabling these polymer simulations and some other exciting features. So shall I move on to the next question? I see a couple of people are raising hand. Mr. Nishant Shukla, what is your
Hello.
question, please?
Hello, sir.
Hello.
Sir, I just wanted to ask the plot which your student was showing us. What does that 5G represent there, sir?
5G is a local electrode potential, the potential that you are applying in your electrode of the supercapacitor. That also depends on your electrolyte specification. For this theoretical investigation, we have considered a standard range of local electrode potential.
And how do you fit your data into that mathematical expression, sir? Do you
See,
choose
as
it point-wise or?
no, we are using simple numerical method following MATLAB.
Oh,
We
okay.
are.
Okay.
I don't think that needs further exploration.
Sure. Sorry for that. Okay, sir. Thank you so much.
Okay. So I guess there was another question from another participant. Yes, I will address the first one by Aparna saying, how do you optimize geometry and method use? Geometry optimization is a very standard method for any first principle based calculation. For geometry optimization, basically you have to give the tolerance limit for your material system. Specifically for quantum ATK, you have to give the pressure tolerance and the force tolerance in your simulation. And also you have to choose a suitable method, DFT method for optimization. The most standard method you will see any literature on DFT is the GGAPB. I hope that answered the question of Ms. Aparna Singh. So I guess Devi Pandirajan, is it a question quantum capacity is possible to calculate in WASP? Yes, it is possible to calculate in WASP as well. Although the GUI is not as much favorable as quantum ATK. This much I can say. Can you give some insight related to the supercell selection for any 2D material? See, the supercell selection basically depends on the application area and the specific investigation that you are performing. Just to give you some perspective, in an experimental scenario, the doping concentration is very small. But if I wanted to mimic that particular doping concentration in my theoretical investigation, the supercell would be abnormally large, and you know the complexity of DFT simulation goes up with your number of atom in the system. So we have to have some trade-off between the reliability of the simulation as well as the computational cost. In my understanding, in most of the cases, 441 supercell or 551 supercell will do very good job to give you a clear qualitative understanding, as well as you can correlate your finding from the atomistic property of your material system, and that can be directly correlated with the experimental exploration as well. Yes, please go ahead. Somebody has raised
Sir,
hand.
so generally the materials like MOS2 and MOS2TE2. So we generally use it to find IVCV characteristics, and we use it to go ion off on the specific characteristics. So that to understand the.
I didn't got the question to begin with. Which material you are referring to? Can you repeat, please?
MOS2 and MOTE2 2D materials like MOS2
Yes.
sulfide and molybdenum Se2 and Te2 materials. So can we get IVCV characteristics, and further we can move into circuit with this software?
I think you can use the NEGF transport tool of the quantum ATK to have the ballistic IV characteristics under the ballistic regime of operation. But if you wanted to look into the mesoscopic transport, that would be difficult to directly get from quantum ATK. You might have to integrate your material property under DFT Hamiltonian into some mesoscopic carrier transport framework. Maybe you can look into some of those open source tools which are available, which offers you this Boltzmann transport equation framework where you can fit in your material Hamiltonian, and you can calculate the IV characteristics.
So
About yes.
open source software like I'm using nanohub.org, which is the open source software for this 2D material simulations. Can you mention any other open source platforms where I can simulate 2D material based devices?
There are a number of software. I mean, the most common one that I can think of, Quantum Espresso. Quantum Espresso.
Espresso.
Yes.
Thank you, sir.
Is there any other question, or is there any other question that I am yet to address? Okay, how to distribute dopant in a structure? See, the distribution of dopant, it is always advisable keep it as random as possible to mimic as closely as possible with the experimental scenario. If you are introducing more than one substitutional dopant in your supercell, keep them as randomly distributed as possible. Because of the finite size of the supercell, it is often suggested by the theoretician who works in close tandem with the experimental group, use different distribution and take an average out effect out of that. That is also a very good strategy to follow. Any other questions? I don't know of any software which can automatically distribute dopant in the structure. That you have to perform manually, I think. At least I'm not. Okay. Oh, that's wonderful. I'm not aware of that. Okay, okay, okay. This is in 2024 version. Okay, okay. I suggest for those who wanted to know the name of this particular tool, it would be available in the builder most likely. You can go through the latest release. If you know the name of that particular tool set, if you can write in the chat box, that would be great because I am not aware of it. So is there any questions on today's presentation or anything else related to apart from the software aspects, on the technical aspects?
Sir, I have a doubt.
Yes, please.
While using quantum espresso, we will give cutoff energy and a cutoff density. In quantum espresso, we are only assigning cutoff energy. Is there any option for why we are only assigning one cutoff actually? Actually, I'm a basic user. Actually, I want to know those things.
Actually, you see the different tool work differently. If you wanted to set up your threshold criteria in WASP, it will be something different. Quantum Etica would be something different. Quantum Espresso would be something different. So my suggestion is you go by the standard value that are used usually in the theoretical literature. If you do a literature survey, you'll be able to see that. For example, in WASP, you have to give the force tolerance, something is in the order of 0.01 EV per angstrom, if I can recall correctly. The specific quantum espresso part I cannot been able to recall right now because it has been some time that I have actively used quantum espresso. Any other questions? So I guess we have covered up most of the queries from the audience. So
So let me share my screen. You can see this is the quantum ETK graphical user interface, that is a virtual nanolab. So here we have created a Markov structure, and in this Markov structure you can see we have to find the element first. So you can type here element. Here you can see first in this structure we have the oxygen and the silicon material. So we have selected the silicon, and then you can go to the substitutional doping, and then you can add your new element, and here you can define the percentage. Suppose you want to add with the germanium and 50%, then you need to click on this preview. You can see 50% of the silicon has been replaced by the 50% of the germanium. You can also select any of the element from this periodic table. And here you can see we have the algorithm like a fixed, fractional, and also we have the normal distribution. If you want to include the vacancy, you need to enable, and then you can choose the element, and then here you can define the percentage. So this way we can create the elemental looping in any of these structure. So may I know, is there any more query regarding this quantum metric software?
Uh,
One doubt.
Yeah, sir, I have a doubt. Actually, if I have a fractional coordinates like COFE204 a structure, in which if I input that shift, it will have a partial fraction around one atom. It will randomly distribute its coordinates, or I have to again go to this builder and I have to make these changes.
Like you can see, we have the prescribed material, and in this prescribed you can see we have the calcium, titanium, and the oxygen. So first you can go with the element, selection of the element. Any of the element you can select, then you can go to the substitutional looping. You can select this fixed fractional, and then you can define the percentage. Any of the element you can choose. Suppose you want to go with the aluminum, you can say aluminum has been replaced 50%. Now you can see we have the calcium, we have the titanium, we have the aluminum, and we have the oxygen.
Thank you, sir.
Yeah, thank you. So I think there is no more query regarding this quantum mechanics. So we would like to extend our sincere thanks to Professor Sayan Kanungo for delivering such an insightful session on the part of the faculty interaction webinar series.
So thank you for organizing this event and inviting us. It is indeed a pleasure to present before you and interacting with the audience. So thank you. We'll be looking forward to getting. My pleasure. Thank you.